Sketch the function f of x using information about la 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 la. Okay, before we dig in, I don't know why this question is in the lesson about slant asymptotes because this doesn't have any slant asymptotes. It's very strangely located, and if you feel like skipping over it for now, there's plenty of reason to do that. But if you keep listening, I will work through this because what the heck, it's here. So, domain. Domain starts out as Ex4, and the only things that can break it are square roots of negative numbers, or division by zero, or some other obscure things like logarithms with bad log-ends, which we don't have here. X squared plus 4 is never negative and it's never zero. It's always 4 or greater, so we don't have any division by zero issues and there aren't any radicals. Therefore, the domain of this is x is any element of the real numbers. For the range, we have a denominator that's always positive, a numerator that can be negative or zero or positive, so on that basis I'm going to say the range is YER. I'll have to keep an eye on that. I'd normally put a little more care into checking the range, but I think this is valid, and if I've made a mistake, we'll catch it down the line. Intercepts. Y-intercepts happen when x equals 0. When x is 0, we get 0 over 0 plus 4, which is 0. Okay, so this thing goes through the origin. And its x-intercepts happen when the whole thing equals 0. So when 2x over x squared plus 4 equals 0. If you're trying to solve that, you multiply both sides by x squared plus 4. X squared plus 4, x squared plus 4. When you do that, these cancel out and you're left with 2x. On the right, you get 0 times something, which is 0. So, again, 0 is the only solution. So the x-intercept is, again, the origin, and there aren't any others. So far, so good. Asymptotes. Vertical asymptotes happen when the denominator goes to 0, and we've said that this one can't. So there are no vertical asymptotes. Is there some other kind? You get slant asymptotes if the degree of your numerator is 1 more than the degree of your numerator, but in this case it's 1 less, so no slants. How about horizontals? We do get horizontals because the degree of the denominator is bigger than the degree of the numerator. And those horizontals are at, let's see, 2x over x squared plus 4. The highest power is x squared, so divide everything by that. And we get 2 over x, and downstairs 1 plus 4 over x squared. Then we do the limit as x goes to infinity. When we do that, the 2 over x vanishes, the 1 hangs around, and 4 over x squared also vanishes. So we get 0 over 1 plus 0, which is simply 0. We do have a horizontal asymptote at y equals 0. Intervals of increase and decrease. Do you still remember how to do a derivative? Because they're back. The first derivative of this thing, df dx, or f prime if you want, comes from here. This is a quotient, so we have to use the quotient rule. And the derivative is going to be bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. Let's see, we get 2x squared minus 4x squared is a negative 2x squared. I'm speeding this stuff up a little bit because you probably know how to do derivatives already, and I don't want this recording to get painfully long. Okay, so there's our first derivative. We're going to need that. I'll get rid of the work in progress here. So, critical values of this derivative come from any place that it's negative, or sorry, that it's 0, or any place that it's undefined. It's never undefined because the denominator is always a positive value. It's never 0 or anything like that. So the only ways this thing can produce critical values is if minus 2x squared plus 8 equals 0. That would mean 2x squared equals 8. That would mean x squared equals 4. That would mean x is plus or minus 2. So those are the only critical values we've got. Again, I'm going to prune this because I've only got so much screen to work with. So let's see how this thing behaves sign-wise. Here is a number line. We have -2 and +2 as critical values. And the pieces of this thing include, should I try to factor that? You could take a -2 out of this. I'm not sure. I'm not totally sure that's worth it. Oh, yeah, okay. Maybe I should have done that earlier. That would have shown me very quickly that the critical values were -2 and 2. X squared plus 4 all squared. Okay, the beautifully factored version of our first derivative is x plus 2, x minus 2 over x squared plus 4 all squared. I'll use this for the sign table. So our pieces are -2, x plus 2, x minus 2, and x squared plus 4 all squared. And then all of that together makes our df dx. Okay, now lots of plus and minus signs. -2 is a fixed number. It's negative all the time. It doesn't care what your x is. X plus 2 goes -0 plus plus plus. X minus 2 is negative, negative, negative. 2 minus 2 is finally 0, and then it goes positive. This thing doesn't know how to be anything but positive. I could have gotten away with leaving that off the table, but I didn't. Okay, so negative times negative times negative over positive is negative. Negative times 0 over positive. Here we get 2 negatives, so that comes out positive. Here we get a 0 again, and then we're back to negative. So this means that our function is decreasing, flat, increasing, flat, and decreasing once again. So the curve's going to go down, flat, up, flat, down, some shape like that. We'll do that in more detail in a while. Okay, so we need the first derivative. I'm going to keep one version of that. We found our critical values. Those are embedded in the table, which I certainly want to keep. And we'll compact that down a little bit. Okay, so we have our intervals of increase and decrease. We have our local maxes and mins. I forgot to mention those. Decreasing, flat, increasing. This right here is the bottom of a valley. Increasing, flat, decreasing means this right here is the top of a hill. We went uphill, stopped, and then dropped again. So those are the locations of our local max and min. And what next? Concavity. The second derivative tells us about that. So let's see if we can fit another derivative in here. This is the first derivative. The second derivative, d squared f over dx squared, is going to be bottom x squared plus 4 all squared times the derivative of the top, which will be minus 4x. That's bottom d top minus, sorry for the multi-line derivative, I don't like it any more than you do, top times derivative of the bottom, and now the chain rule kicks in and this gets a little messy. 2 times x squared plus 4 to the 1, and then chain rule fires and we get a 2x out of there. And all that is over the bottom squared, which is going to be x squared plus 4 to the 4th. All right, I'm going to lay that all out in one line if I can. I don't want it to look so crummy that you can't even follow it. There's that, and we'll get the denominator. Okay, that's halfway passable. Okay, so this is working from our first derivative, bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. And now I will painstakingly clean that up. This x squared plus 4 is going to be a common factor. I want to pull that out. Do I want to do that right away? I think I will do that right away. I'm going to factor out a single x squared plus 4. There might be other common factors. I'll get to them in a moment, but I want one of these out right away. With that gone, this first term is a single x squared plus 4. The other one got factored out. And then a negative 4x. I'll be multiplying these together in a moment. Then we get the big minus in the middle. Then we have minus 2x squared plus 8. This x squared plus 4 has been factored out, so we're just left with 2 times 2x. I'm going to write that as 4x because I just barely have space for that, I think. And all of that is over x squared plus 4 to the 4th. Good so far? This is an above average annoying derivative, but it's nothing super extraordinary. We have to slog through this kind of thing fairly often in calculus. Here we catch a bit of a break. We have x squared plus 4 in the top and in the bottom. So I'm going to cancel that out. I'm going to cancel one of these x squared plus 4's out. We now have 3 remaining. That helps a little bit. So in our next line, negative 4x times x squared gives me minus 4x cubed. Negative 4x times 4 gives me negative 16x. And now, negative times negative 2x squared gives me positive 2x squared, times 4x gives me 8x cubed. And now we get to do that again. Negative times 8 is negative 8, times 4x is negative 32x. And all that is over x squared plus 4 to the 3rd power. Collect like terms. We get positive 4x cubed minus 48x over x squared plus 4 to the 3rd. And there's a common factor of 4x in that numerator, which we can pull out, leaving x squared minus, please let it not be a perfect square. Good, it's not. Okay, so there is our factored, finished, cleaned up second derivative. Now that I have it, I'm going to clear away the work in progress because I need the space. And I'll just take our finished form here. Good, okay. So there's our second derivative, about as factored as we can get it. And using that, we have to find critical values, and then we'll see what our concavity is up to. So, is this thing ever undefined? No, it's not, because this x squared plus 4 is continuing to protect us. This is always a positive number, meaning it's never 0, meaning we never get any division by 0 problems. Also, there are no roots in here, so there's never any place that this is undefined. Is it ever 0? Oh yeah. It's 0 if 4x equals 0, which would mean if x equals 0. It's also 0 if x squared minus 12 equals 0, which would mean x squared is 12, which would mean x is plus or minus root 12, which cleans up to plus or minus 2 root 3. So, 3 critical values we have to look into. Time for another sign table. We have minus 2 root 3, we have 0, and we have positive 2 root 3. I believe this function has odd symmetry, and if I had checked that ahead of time, it might have saved me some work by now. Because then, like, you find that there's a critical value at 2 root 3, and you know there has to be another one at negative 2 root 3. But they didn't ask for symmetry, and I didn't think to check, so I will do penance by getting by without it. But I do want to state for the record that symmetry is your friend, and it can save you some trouble. It is worth looking for, usually. Okay, so the pieces of our second derivative are 4x and x squared minus 12 and x squared plus 4 all cubed. And all those things together make, I'm just going to write f double to save a second. So if x is lower than minus 2 root 3, that means it's a negative number, and 4x is negative. Negative again, negative again. When x is 0, 4x is 0, and then this goes positive. Easy enough. If x is like minus a million, then x squared is a trillion, take away 12, and you still have a positive value. If x is exactly minus 2 root 3, we know that this piece equals 0. And then this goes negative. This is a parabola after all, so we kind of expect it to go positive, 0, negative, negative for a while. Then it's 0 again, and then it comes out positive. X squared plus 4 is always positive, so this last row is very easy, and if you leave it off your table, it won't even hurt you, because positive numbers don't change things. So if we have negative times positive over positive, that comes out negative. Negative times 0 over positive, that's 0. Negative times negative over positive. 0 times negative over positive. Blah, da, 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 da. 0 over positive, and all positives. So this means that our function is concave down, concave up, concave down, concave up. It's pretty bendy, and that means the points in between where it changes from concave up to concave down are what we call inflections. I write inful for inflection point. A lot of people write POI for point of inflection. That's perfectly fine also. Okay, so now that we have that, we'll do our space clearing ritual one more time. Squish this down a bit. Good. Okay, so intervals of increase and decrease, got them. Local maxes and mins, got them. Intervals of concavity, got them. Points of inflection, got them. And using all that, they ask, try to sketch it. All right. We don't have a great many points plotted for this thing, but we do know that it goes through the origin, so okay, we'll take it. I guess another thing they asked for was the maximum and minimum values, and while I found their x coordinates, I never did find their y's, so we could knock those off. If x is negative 2, we know that's a local minimum. The y value would be, what is it? Negative 4 over 4 plus 4 is 8, so minus 1/2. So we have a local minimum at minus 2 minus 1/2. Over here at 2, where the function increases, is flat, and then decreases, that's the top of a hill or a local maximum. So let's see what that's about. X is 2. Up here in our original function, we get 2 times 2 is 4 over 4 plus 4. It's going to be 4 over 8. Yeah, it's positive 1/2. See this again? Minus 2 minus 1/2 plus 2 plus 1/2. This thing is really behaving like it has odd symmetry. So there's 2 more points we can plot. I'll get those onto our sketch. Minus 2, that would be minus 1, so minus 1/2 is about there, and that's a local minimum. I'll just put a little bit of a bottom of a valley shape there to remind me. When x is 2, 1, 2, we're at positive 1/2. That's local max, so we'll put a little bit of a top of the hill curve there to remind us what's going on. The intercepts have nothing more to tell us. There aren't any vertical asymptotes. There is a horizontal asymptote at y equals 0, so let's get that in there. Out here, when x gets very large indeed, positive or negative, the function will flatten out and hug the x-axis. Intervals of increase and decrease. The function is decreasing everywhere below -2. So this is -2 right here. The function's decreasing all the way up to -2. Then it increases until we get to +2. After that, it decreases again. So that's all the information we got out of our first sine table. The second sine table tells us it's concave down until -2√3, which is like -3.4-ish. 1, 2, 3, somewhere around there. That's -2√3. Our function is concave down until we get to there. Then it becomes concave up and stays that way until 0. Concave up, concave up, concave up. Then it's concave down again until we get to +3.4. But there's the cutoff. And after that, it resumes being concave up. So, stretch, crack your knuckles. Let's see if we can draw a curve that satisfies all that. Out here, way on the left, the function has to follow the x-axis. It has to be decreasing, it has to be concave down. Decreasing and concave down looks like this, right? Going downhill and curving even more downhill. So there's our decreasing concave down shape. It keeps doing that until we get to this point. Now it's decreasing and concave up, which means this kind of curve, like the bowl of a spoon. So I'm going to try to draw that. I'm just going to blip that and try to draw a nicer version. Decreasing concave down, decreasing concave up. We get to our minimum. Now we're increasing and still concave up, like so. We have to go through the origin. After the origin, we're increasing and concave down, which looks like this. Top of someone's head. Increasing concave down. That keeps being true until we get to this local max. Then we're decreasing concave down, which looks like the other side of top of someone's head, dropping this way until we get to our, what was it, 2√3. Then we go decreasing concave up, which looks like, again, bowl of a spoon, and the horizontal asymptote starts to take effect here, so we need to get very close to the x-axis without ever touching it, if we can. So that's our curve. It's a little hard to see the curvature here, so I'm going to draw that again kind of quickly, but I'll blow up some of our existing work to make room. What you should see is, if this is the x-axis, it should be decreasing concave down, decreasing concave up, increasing concave up. Sorry, I didn't give myself enough room to do that. Let me try that one more time. Okay. Decreasing concave down, decreasing concave up, increasing concave up, increasing concave down, decreasing concave down, and decreasing concave up. So those are all the segments that this thing had. decreasing concave up. Here we had, yeah, decreasing concave down. That's the part I wanted to show. So it's a lot. I found when I was learning this, it helped me to do this at the top of the graph. Mark down all of your requirements for the increase decrease, all of your requirements for the concavity, and then just take care of them one at a time. If you've gotten all of these correct, and if you have a couple landmark points, that's usually enough to get you through it.